Thank you, Omar. All right, good morning, everyone. So we have a selection of people studying. So tell me what you're studying, students here. Shout out a few courses so I know who I'm talking to. Sound and video. Any advances on? Right. Okay, so sound. Okay, so quite a few audio people, some general sort of media stuff. Okay, what I'm going to try to cover here is looking really at the front end capture parts of the project, and I'm going to try to touch both on the audio and the video aspects, although my colleague Rob from Salford will be going more into the audio side of things. Hopefully there'll be something here maybe that'll shed a bit of light on both conventional production, the way things happen at the moment, and the way we'd like to see things advancing a bit in the future. So hopefully this will be sort of generally enlightening about broadcast technology in general, as well as some of our particular advances. So as Georg mentioned in his presentation, we're looking at some of the ways that TV media production delivery could advance in the future. So we're seeing proliferation of small devices, but of course also larger devices coming along. One of our project partners is working on this, what they call the Time Lab, Tomorrow's Immersive Media Experience, which presents a 180-degree panoramic video display, which really gives you the feeling that you're standing there in the place where things were captured. You've got video filling pretty much 180-degree field of view. And of course, not just in the video side of things, but audio is getting more advanced. We're seeing people developing spatial audio systems where you get audio coming from above and below as well as all around. And there is also some interesting work going on in ways of delivering media in a sort of much more immersive way. And I'm just going to take the opportunity to show a little bit of work that my colleagues and I at BBC R&D did a few years ago on this. We were looking at the idea of how to present really immersive video to people in the context of a living room without necessarily having to build a huge panoramic display. And this was an interesting way of looking at the way sort of video could evolve. And the idea, in the same way as putting surround sound in to replace a stereo loudspeaker system, so you suddenly get sound all around, but you're looking at the same picture, we thought, what could we do to make video more immersive if we had a panoramic video system that was capturing video, and we knew how that video related to the view on the main TV screen? Could we use it just to extend the field of view of people? And we had a little bit of fun shooting material with two cameras, one with a fisheye lens, one with a standard lens, and then presenting the video from the fisheye lens projected from a projector onto a curved mirror that then got splattered around the walls of the room. And this gave a very sort of immersive feeling. Basically, as objects left the TV screen, they would then continue out across the walls of your living room. Interestingly, there's been a number of other people who've more recently looked at this. I don't know if anyone's come across Microsoft's Illumi Room project, which again uses a projector and sort of takes video games from consoles like the Xbox and projects those around the room. This was a bit of an experiment as to how you might do that in the context of video production. So it sort of shows one of the approaches where media could really extend beyond just a conventional screen. So one of the challenges is, if you're going to produce content like this, how can you do it in a way that extends existing production technology and allows you to produce content that could be used for everything from small mobile phone type device up to some kind of sort of large immersive experience like this. So I thought it's worth having a little look first at how video is produced at present, and I'm going to show you as a sort of little case study the way my colleagues in our sports production area cover Wimbledon every year. Here is a ground plan of Wimbledon. You can see the various tennis courts dotted around the place. And if you were to look at one of those courts in detail, you'd see there's something like 15 cameras all covering different aspects of the court. They're all high-definition cameras, wide aspect ratio, 16:9, with the format of those cameras chosen because we're making a 16:9 HD broadcast. We don't necessarily know where they all are. I mean, not exactly. I mean, we know one is giving a long shot of the court, one is perhaps on the sideline, but you don't know their position or orientation to any great accuracy. The videos go into the outside broadcast truck. This is one of the largest outside broadcast trucks in the UK, known as OB1, and it's so large that even the expanding sides have expanding sides. Inside, there's a large production gallery area where the production team can see feeds from most of the cameras, and they've got the usual preview and sort of on-air pictures. And there's a huge bunch of cables that go into the side of the truck, bringing in all the audio and video feeds from the various parts of Wimbledon. And this is only one of a number of OB trucks they'd have there. There's probably a truck covering almost each of every court or every pair of courts. And of course, the most important thing to keep everything going, the good old BBC T-urn. So if we wanted to go from that kind of production through to somewhere where we can really use the captured audio and video in a much more flexible way, one approach we've been developing in the FascinatE project is the idea of what we've called a layered scene representation. So we're not just treating every little audio and video signal as something that we can edit together to make a final program. We're trying to keep the data throughout the production process. So this means knowing the positions and orientations of cameras, the locations of the microphones, try to keep the separate feeds from these separate right until the moment you need to combine them to put together something that somebody's actually going to see. That means that you can tailor that combination process to the kind of device they're using, maybe to their personal viewing preferences, which shots they want to see, and the capabilities, say, of the audio device. Am I doing something for mono, stereo, 5.1, or a wonderful big surround system? So there are some interesting things that you can do if even just with basic camera metadata. And as an example of that, we did a bit of work at Wimbledon a few years ago looking at if we knew the exact position and orientation of the cameras covering the main court, you could do some more interesting ways of providing transitions from one court to another. Rather than just saying, oh, now we're going to cut from court 3 to court 1, you could actually fly. And you could build a nice 3D model that represented the entirety of Wimbledon. You could register the video from each camera into that model, and you could fly out from one camera, fly across Wimbledon and fly into another, because you now have those cameras registered accurately with your model of the court. And we actually did a trial of this that went live on air. I sat in the back of an OB truck with a bit of prototype software, and this very finger pressed the space bar on the bit of code, and you think, God, I hope this doesn't break, because there's 20 million people watching now. And just as an example of sort of the behind the scenes on that, I've got a little video here which explains the process of trying to measure where the cameras were looking by tracking the lines on the tennis courts. We worked with a company called Crystal CG who built a nice model of Wimbledon, and it all got seamlessly blended together. Oops, let me try pressing the right button.
Keep you up to date with it, of course, here on BBC One, but also if you want to continue watching, you can by pressing the red button.
So that was an example of where if you know positions and orientations of cameras, you can start doing some interesting things. Another example of some related work we've been doing that again has relied on knowledge of exactly where the cameras are is looking at trying to reconstruct a 3D model of what's happening, say, on a football pitch. If you've got 6 or 8 camera views, you know where each camera is, you can align the cameras. So here we have a set of views from the cameras. We can identify where the players are by using a nice simple technique, say chroma key, to pick the players out against the green grass. We can then, knowing the positions of the cameras, we can essentially work out where or what the rough 3D position and shape of all these players are, because you can see a silhouette of a player from this position, and from the camera over here you get another view, so you know he must be in this volume, and the more cameras you add, the more precise you can make the silhouette. That allows 3D models of the players to be created. You can then overlay the textures from the video images on those players, and you can produce a scene that you can then fly a virtual camera around. And we've looked at this, for example, for allowing sports producers to provide a really close-up analysis of the action from different viewpoints. And as an example of that, here's a test we did for a football match. So you'll see it switch from a real camera to a virtual camera, move the viewpoint around. The kind of thing that you could do if you had a camera on a cable system flying over the area, but that was all done just with the video from the standard cameras. And a similar bit of work we did for rugby. So this is showing flying down to pitch level and then flying a view across from one camera to another. Here we've built a 3D model of the stadium in which we place the model players. So we're relying on the live camera video to give you the player models, but the basic stadium itself stays fixed, so you can sort of make a one-off model of that. So all clever things you can do if you know more about the scene. You're not just taking the video, switching from camera to camera and broadcasting it. So that brings us on to the concept of the FascinatE project itself. And as Georg mentioned at the start, we're looking at a range of capturing devices. So the pan, tilt, zoom broadcast cameras, as you've seen in some of my earlier examples. The fixed omnidirectional panoramic camera that can provide support for not just those high-end theatres where you'd have, say, a 180-degree field of view, but also allow viewers to interactively pick out different parts of the scene, zoom in, follow objects, etc. And then the audio equivalent of that with a range of microphones to allow us to find essentially individual audio sources and maintain those through the production process. And the idea is to keep all that in a calibrated, registered reference frame. So we've got what we call a layered format agnostic representation of the scene with all the data sources and all the video and all the audio, but not yet mixed together. The mixing together happens later. So we thought we'd, in fact, quite near the start of the project, must be getting on for 3+ years ago now, we did a first test shoot, and we went to Chelsea's football ground at Stamford Bridge in London, and we negotiated with the BBC Sport production people and the ground staff at the match to bring in the big panoramic capture camera that we were going to use for video, and to record all the additional audio feeds, and to bring in some extra microphones. So you can see here the big panoramic camera system. I'll be giving some more details of that shortly. One of the problems we had with this was actually negotiating to bring it in so that we could set it up, because it's quite big. It's about this high. It's got 6 large mirrors with an array of 6 cameras below it. And if you put that on a standard camera platform, it tends to block the view of the people who sit behind it. And the single biggest problem we had here was with the guy who was in charge of the grounds saying, oh, the guys who sit behind the camera positions, there's a lovely guy there who's got a season ticket, but almost every match he emails me and says his view was blocked by the camera operator, and why do all these cameras have to be around? And if you put that thing in front of him, God, I can imagine the complaints I'm going to get. So we had to sort of squeeze it back out of the way, and then when the crowd came in, our colleagues from HHI in Berlin who developed the camera had a nice little chat with the guys in the seats and eased the camera out a little bit to get a better view. The audio side of things that Rob will talk about a little bit later, we got individual feeds from all the gun microphones based around the pitch. We had a sound field microphone, which, the audio people, have you guys come across sound field microphones? Yep, good. Yeah, a few people know about them, and a conventional stereo pair. And also, we had, and I think I have a picture of it, something called an Eigenmic, which is a sort of tennis ball-sized microphone capsule with, I think, 32 different capsules on it, which allows you to produce a higher order ambisonics representation of the scene, which for people who haven't come across that before means that you've got enough raw data to allow you to reproduce the sound field to quite a high accuracy, so you can get sounds coming from above and below, and you can feed these into different configurations of loudspeakers. So as a part of the layered scene concept, we needed to make sure we measured the position of all the cameras and microphones. So we did that using a laser scanner. Now this is a device often used for scanning buildings, for architectural kind of purposes, on film sets to provide accurate reconstructions of the way a film set's been created, to make it then easier to add graphics and other things in post-production. And actually, it was quite a fun thing to look at the results that it produced. So it basically has a scanning laser beam which gradually rotates around through 360 degrees, and the laser uses a time of flight process to measure the distance to an individual point, and also gets the RGB colours of that point. And that allows you to produce a rather nice model. So here we have a 3D model of Chelsea's football ground. This was actually pieced together from, I think, 6 or 8 separate laser scans from different places. You can sort of guess where the scanners were placed. You can see these radial curves sort of emanating from the positions where the scanner was. So each of the sort of 3D voxels in this model, the positions of those are known to an accuracy of something like a millimetre or a couple of millimetres in space. So with that, you can measure exactly where the cameras were, where the microphones were, the position of the pitch, the location of the audience, and so on. In fact, we found that provided much more data than we actually needed. So for some of the later test shoots, we just went in with a laser theodolite device called a total station, which you can basically point at something, press a button, and it gives you its X, Y, and Z coordinates. And for just getting microphone and camera positions, that actually proved to be roughly sufficient. So I said I'd say something about the panoramic camera. And this is a key element to the way the FascinatE project wanted to develop things, because unlike a conventional broadcast camera that will give you a fixed aspect ratio and enough pixels, just enough pixels for what you need, we wanted to have something that would give you a wide angle of view and a high resolution in a way that you could sort of repurpose that for a wide range of different viewing devices and viewing preferences. So I'm just going to have a little look at the history of panoramic video, and people have been playing around with cameras to provide wide fields of view for a long time, and from these examples apparently going back to the World Exhibition in Paris in 1900, all the way through to some of the work that our colleagues in the FascinatE project have done with their immersive projection system in their labs in Berlin. So there are a number of different ways of putting cameras together to try to acquire panoramic video. There's some examples here, and if anyone's come across the Ladybug camera, it's one of the commercially available little cameras that has a number of firewire cameras in a little block about this big, designed so that you can stitch together a sort of spherical image from them. Various other examples. There's a system here produced by a company called Camargus, where they have, let me count, 2, 4, 6, 8, 10, 12, 14, 16 HD cameras arranged in a ring looking in, which you can use to build not a full 180-degree system, because if you tried to do 180 degrees, you'd find the camera on one side could see the camera on the other. Alternatively, there's the mirror-based system, which our colleagues in the FascinatE project have produced, where you have the cameras actually looking up into this mirror fan arrangement. And that has certain advantages that I'll go on to cover. So the sort of obvious way of doing it would be to have a bunch of cameras looking out, and this is essentially what you'll see like on the roof of a Google Street View car. That's fine if you're viewing things that are generally a long way away, but because you can't get the optical centres of the cameras very close, it's then difficult to stitch together the images and have something that looks seamless for objects at a wide range of depths. So the theoretically optimum approach would be to put all the cameras physically coincident, but of course you can't get more than one camera into one bit of space. So hence you do a trick with mirrors and try to arrange that optically the centres of the cameras are very close, even if the cameras themselves are separated. So this helps to overcome some of the limitations of the sort of Google Street View outward-looking star-like approach, that because here the separation from the camera lenses can be quite significant, you find that with objects less than, say, about 10 meters from the cameras, you find that they will either start appearing in very different places in the image, or potentially maybe being missed completely if they're, the closer they get to the cameras, actually they're not visible in any of the cameras. So hence this mirror-based approach. Now, one of the developments that we've been looking at in the project is not just how you position the cameras, but also what kind of cameras to use. Some of the first work that was done, in fact, in that football example I showed earlier, used some very small format, sort of micro HD cameras, single CCD with a small lens. And there are all sorts of inherent problems with physically small cameras, small lenses. You get the optical quality just isn't so good. You've got a sensor, a small sensor with a Bayer pattern on it, which means you've got individual pixels have red and blue and green filters on them, and if it's a small sensor, you haven't got enough pixels to overcome both recovering the colour and getting a good resolution. Another interesting problem that arises when you're capturing a panoramic image is because you're looking at the scene in such a wide, over such a wide angle, you'll find you get a huge range of brightnesses. You look at any typical scene, particularly outdoors, you'll get parts of the sky that are brightly lit. You'll get areas of the ground that have got sun shining on them. You'll have other areas that are in shadow. Now, if these are being covered by a conventional camera crew, you've got a guy in the OB truck, usually called the racks operator, because he's sitting next to a large rack of equipment, I guess, operating the iris to the camera and trying to keep the exposure correct. So as the camera pans from a brightly lit sunny area into a shadowy area, he can make adjustments. But if you've got a wide-angle camera that's trying to cover the whole of that area in one go, you really need to be able to have a camera with what's called a high dynamic range that can cover that full range of brightnesses. Even if later on you reduce the brightness range to fit a conventional display, but you can do that based on which part of the panorama you're looking at. So this camera has actually been built with cameras from another partner in the project, ARRI, who are well known originally for making film cameras for cinema production. They've now moved into electronic cameras, as everyone else has, and the Alexa is their latest electronic camera that's been used for filming, I think, large numbers of sort of recent big cinema blockbusters. It's one of the most highly regarded professional electronic film cameras you can get. And it has the advantage of being able to capture scenes with a high dynamic range. I'm always amused when I look at this because I feel that this is testing the fabric of space-time, because those cameras are not cheap. And you wonder about, how much money can I get into one bit of space before something starts collapsing? And you've got 6 ARRI Alexa cameras there, which I guess have to be quite closely guarded. And in fact, one thing that ARRI did in the project, in order to try to reduce the bulk of that camera system, was to separate the front capture part of the camera from the back-end electronics. So actually, those cameras there only have the sensor and the processing electronics that have to be immediately around that sensor. The rest of it is on the end of an optical fiber and can be sit sort of up to, I think, 100 meters away from the place where the capturing is actually happening. So once you've got your video from your 6 cameras, you need to be able to process these and stitch them together. So our partners in the project have developed something they call the real-time stitching engine. It takes these 6 HD video streams from the different cameras, and it will do the geometrical correction, in other words, compensating for things like lens distortion and the exact position of the mirrors. It will compensate for the photometric calibration of them, adjusting the relative brightness and color rendition, stitch them all together and provide a nice panoramic video, which in this case has a resolution of 6,000 pixels horizontally, 2,000 vertically. So just to go through some of those processing steps, here are the 6 images that would come out of the system raw. You'll notice that these are widescreen images that are placed on one side in order to give the 2K panorama height and 6K pixels horizontally. So the first thing to do is to do the geometric correction, compensate for lens distortion, the relative positions of the cameras, and so on. Then deal with the colorimetric aspect. So we've now got the same color of green grass everywhere. And then crop that to give the completed 6K by 2K panorama. And there's a lot of detail in that. If we look at one part of that, you can see that we're not just picking out the wide angular range, but we've got very good resolution when you come to look at a small part of it. And as I explained, they now have a real-time system for stitching that together. Amazingly, they're getting these 6 HD video streams into one PC using 3 HD video capture cards, each with 2 inputs. Then they're using the graphics processing power of a GPU to stitch those together. And they can do all that in real time to produce a panorama that you can actually interactively zoom in and pan around. And since that new camera with the Arri Alexas has been put together, we've shot a number of demo productions in addition to that first football match. And you'll see some of these in use in some of the demonstrations that you'll see throughout the day. One was a dance performance in Berlin in May last year, set in, I believe it was a large old bus garage that is now used as a sort of performing arts area. And there was a large dance production staged with amateur dancers, but with the Berlin Royal Philharmonic or Berlin Philharmonic Orchestra providing some music from Carmen, which accompanied that production. And then staying on a musical theme, my colleagues and I arranged for the camera to be taken to one of the BBC Proms concerts in the Royal Albert Hall last summer, and that produced some very nice, very high quality footage where you really got the feeling that you were standing in amongst the Prommers experiencing the concert. I'm going to talk a little bit now about the different imaging systems that we have in the project. So we talked about the panoramic camera, and of course we had the broadcast cameras. But I made the point that the FascinatE project is all about making sure that we've got everything in the same reference frame. We know the relative positions of all these cameras. So we should be able to let each camera play to its strengths and use them together in a flexible way. So although we said that the panoramic image is of a very high resolution, it's worth looking at if we were to zoom in on a part of that panorama, picking out a very narrow angle part of it. And you'll see in this image that if you really try to squeeze it tightly, you won't get out the kind of detail that you would get, for example, from a broadcast camera with one of these long zoom lenses on it. And so that's an equivalent image covering that tiny part of the scene that a broadcast camera could pick out. And what's more, of course, that's a 1920 by 1080 HD image being displayed on a PowerPoint slide, so the actual detail in that is a lot higher. So here we can read the name on that player's chest, whereas in the panoramic image you can hardly distinguish the player from the background. So clearly that we felt there ought to be a way of exploiting the detail that you have from a broadcast camera, which after all is going to pick out the most interesting parts of the scene, because there's an intelligent camera operator pointing it at the parts that are really going to be of most interest. So we did a little bit of work seeing whether you could, for example, take the detail from the broadcast camera and use it to enhance the resolution of the panoramic image. And it turned out to be not quite as easy as you might expect. So here we have the Omnicam image, and I've picked a part of this where we had a close-up broadcast camera covering part of the scene, and it'll be the area with those players in the top right-hand part there. And if I simply overlay the image of the broadcast camera, yes, you can see it's a lot sharper, but you start noticing several other problems. So first there's the photometric calibration, the fact that the color rendition is different. There's also a parallax effect. Remember, I talked about how important it was when we were stitching the Omnicam images together to have all the cameras as close as possible. Here, the broadcast camera was several meters to one side of the Omnicam. And although we were looking at objects that were, I don't know, 50, 60, 70 meters away on the other side of the pitch, that shift is still very significant. Now, some of these issues can be dealt with relatively easily. There's an approach which can be used to automatically match the colors from one image to another, a process called histogram matching. You essentially look at the histogram of the occurrence of red, green and blue in one image, and so 70% of the image uses this particular kind of green and so on, and you can then devise some lookup tables that will give the image you're trying to match exactly the same color histogram, and as long as they're looking at the same scene, that will then give you a very good color match, so you can you can hardly distinguish the grass in those two images. Yet we've still got parallax issues because the images are coming from different viewpoints. And if I switch back to the Omnicam image, you'll see the position of the players shift. Now, one thing we looked at is, because one of the use cases of this would be a user who's got the panoramic image saying, oh, I'd like to look at what's going on over there. And the system knows, aha, I have a close-up camera covering that bit. So instead of just zooming into that region in the Omnicam image, as I zoom in, I'll switch to give the user the nice sharp broadcast view. So one thought was, if we've got these parallax problems, can we work out which object in the scene is actually the visually most important, the one people are going to be looking at, and make sure that we line those up. So here, we're probably looking at, for example, the player in the middle who's about to receive the ball. And if we do that switch, you can see player 12, he stays pretty much in the same place, and you may not actually have noticed that the background shifted. I'll switch between those again. So if you look at player 12, he just gets nice and sharp. If we look at some of these players, say the player in red on the right there, actually that's the ref. He's staying in roughly the same place because he's probably at about the same depth. But say player number 20 here, who's closer to the camera, he moves quite significantly. But if your eyes are on the center player, the theory goes that actually you can do the switch without people noticing. And I have a little video that will illustrate that. So here we've simulated a zoom from the wide-angle Omnicam image, and at some point we will transition to the broadcast image, and we hope that we've lined up the depth of interest correctly so that the viewers don't see the transition. So here's our wide-angle image. We've got the interesting players over there with the ball. We zoom in, and there's a sort of semi-seamless transition. So that's part of the work that we're doing, trying to find nice ways of integrating and using each kind of image for its own strengths. So that's taken me through the video part. So what I'd like to do now is to hand over to my colleague Rob Oldfield, who's going to tell you about the audio side of the project. And there will be 30 seconds of fumbling while we swap microphones.
Okay. Yep. Fumbling over. Great. So the principle for audio in FascinatE is actually very similar in ethos to the principles of video capture. We want to capture all of the jigsaw pieces, if you like, in order for the user to kind of put the scene back together again. So it's about scene capture rather than just about kind of capturing a mix, as would be a case in a normal scenario where you would have a sound engineer at a desk and he would be mixing all of his available mic feeds to produce either a stereo output or a 5.1 output or a mono output, whatever is available. So we want to be able to broadcast sort of all the raw ingredients, if you like, that sound engineer would use. But rather than transmitting all of the microphone feeds, which could be rather confusing and potentially not that useful actually, we need to go down a different approach. And as part of the FascinatE project, what we're looking at is an object-orientated approach to audio, where we capture specific audio events that are happening within the scene. So in a drama, it would be somebody speaking. In a football match, as I'll talk about in a minute, it would be the sound of somebody kicking a ball or the referee blowing a whistle. But those audio events, if we can capture, firstly, what they are in terms of the content, and secondly, where they are in the scene, then it allows us to broadcast those audio objects and then put them back together at the user end to produce a 3D sort of scene and give them the sense that they're being there. Now, of course, it's not all about the audio objects. It's additionally about the sound field, the ambience. If I was doing a football match and I just did ball kicks and whistle blows, it would sound incredibly boring and not very realistic. It wouldn't give you any sense of immersion. You wouldn't feel like you were part of the scene at all. So additionally, we need to broadcast the sound field. So the sound comes from all different directions. We can sample it at maybe one specific location or using an array of microphones, which give us an idea or a recording of the ambient sound, which we can also have a bit of a play around with, as I'll talk about later in the reproduction presentation, which is actually this afternoon. So in terms of advantages of this technique, it allows us to be fully immersive at the reproduction end. So we've got all our jigsaw pieces, and we can move them around in real time. So if you're navigating within the panoramic image that Graham talked about, then you'd want the audio to match up with the visual, your visual perspective. So if you're looking at this particular goal and somebody kicks a ball over here, that's where you want to hear it from. But then if you're looking at that goal, you'd want to hear it coming out of your right loudspeaker. So doing it objectively means that you can have that sort of interaction and you can create the right audio perspective no matter where you're looking at in the scene. It also provides us with a format agnostic approach, which of course is the core of the FascinatE project, in that it doesn't matter which audio device you've got, whether you've got a pair of headphones, whether you've got a simple stereo or many loudspeakers or wavefield synthesis or ambisonics, whatever you've got, we are providing the pieces to be able to decode that into whatever reproduction system you've got. So a bit more then about this sound field capture that I mentioned. So we principally used an eigen mic and also a sound field mic. I always think of an eigen mic as a bit like a sound field mic on steroids. So a sound field mic traditionally has got 4 captures, whereas an eigen mic's got 32. It's the daddy of all spatial audio microphones. And it may look simple, it may look like just a board with lots of capsules on, but there's an awful lot of processing that needs to go on in order to encode that sound field, to encode the sound incident from all different directions into a format that can not only be broadcast, but that can be interacted with, that can be rotated and what have you. And there's a lot of issues to do with the sound diffracting around the sphere and whether you've got a closed sphere or an open sphere that have to be solved. And my colleague Holger will talk a bit more about that this afternoon. So significantly though, we're capturing height information. Now most audio systems that you're probably used to at home or even in a cinema currently mainly deal in the sort of listener plane, which is a good idea because we've got 2 ears that are co-located on that plane. So we're generally much better at localizing sounds in lateral directions. But it's amazing how much difference it can give you to your audio perception if you also include some height information. So even though we're not as good at localizing vertically, it's still very important for our perception of a natural space. And a good example, if you listen to our audio demo out there, we've got some of the footage from the proms and also from the football match. When you sit amongst the 16 loudspeakers that we've got, the sense of sort of envelopment really increases with having your vertical and the loudspeakers from the floor. And we did a recording of the football match down at Chelsea, and when the loudspeaker system comes on, you know, appears from above your head, goal scorer number 22, and you really feel like you're part of the scene. So that's a significant aspect of the sound field reproduction that's important, as well as allowing people to change their tilt angle as well as their pan angle within the panoramic image. So this is just a bit more mathematical detail just to make us look more intelligent. So we've looking at the Eiger mic there that decodes the sound into this spherical harmonic components, basically telling us what intensity comes from each different direction. We encode it into this fancy equation, and then it allows us to actually decode it to whatever audio system we've got, allowing us to do those rotations and whatever to match the viewing angle. So, audio object capture. I said that we need to provide all these jigsaw pieces. We need to provide our listeners, our users, with all of the audio sources in order to put the scene back together again. So this would be really easy in a modeled situation where you could just put a source there and you could put another source there in some kind of computer modeling application. But in a real world scenario, we need to record the scene. We need to record who's making what noise when, what machine's making a noise, and where in the scene is it. Provides us with some interesting challenges because we don't have an infinite number of microphones, strangely enough. So we have to kind of make do with what we've got in a kind of broadcast sense, maybe add in a few additional microphones that can help us out. But traditionally we'd have sort of our kind of capture options are close microphones or shotgun microphones, so very, very highly directional mics, which allow us to kind of say exactly what's going on in a particular direction, but hopefully don't let us hear anything that's happening either behind or to the side. And so we've got arrays of microphones, or we've got these close or shotgun microphones in order to kind of figure out what's going on. So one of the kind of principles that we've been applying is a kind of feature extraction algorithm. Can we look at what the audio feed is to figure out whether something's interesting? And if it's interesting, whereabouts is it being interesting? So where is the person talking in the scene? Or where is the sportsman running around the field? So we have a look. You could either do this in several different ways, and we kind of we would split audio objects into two categories of either being implicit or explicit. So just to define those, an explicit audio object would be something where it's got a very defined measurable position. So if we put a little tracking device on someone and we had a microphone like this one, then I could be an explicit audio object walking around and you could track me, and that would be hunky-dory. You just have to sort of transmit my position information and my recorded position. That's kind of our easy case. The more complicated case would be an implicit audio object where we have to kind of figure out what's going on. So we're using our available microphones to figure out where these sources are and to track them using other sources, such as some audio processing or what have you. And so these audio objects are what we can use to put the scene back together at the user end. Now, interestingly, we're no longer just transmitting audio, we're transmitting audio along with this associated metadata. So primarily it's audio information, audio content and position, but there might be other metadata that could be useful, which could feed in to some of the visual side. So is this a particularly interesting thing? Is this a particular player? Which part of the crowd is loudest? Things like that. We can also transmit that data, or how sure are we that this is interesting? If we're really sure, then we might want to turn that into a view that somebody might want to sort of subscribe to and go, I want to look at everything that sounds interesting. And then we can give them the ability to do that within the panoramic image. So a little case study. Again, I'm looking at this match that we recorded at Chelsea. This is the sort of regulation microphone setup here, apart from with the addition of an Eigen mic and a second sound field mic that are our additions. So you can see we've got these 12 very highly directional shotgun microphones around the pitch, and that capture the on-pitch sounds. And if you go into one of these OB vans whilst there's a football broadcast like this, you'll see a guy who's frantically juggling around faders, and what he'll be doing is only raising the faders into the mix when the action goes into a specific location on the field, so he doesn't pick up too much crowd noise. If you put all those microphones into the mix, you'll find it just like a wash of people shouting abuse at other people and general crowd noise that you get at a football match. So that's obviously not a completely ideal situation. And this is actually one of the other applications of some of the work we've been doing on the FascinatE project, is if we can extract the sound sources on the pitch as audio objects, it means that we can actually automate this mixing process, and we can save somebody getting repetitive strain injury by juggling these faders around. So it's got a humanitarian angle to it as well. So we've got those 12 shotgun microphones, and then we've got our ambient sound field microphones and a stereo pair, so we can pick up some of the crowd, because crowd noise is our friend. It's just we don't want too much of it, so we want to be able to control it using our stereo pair or a sound field microphone if we want to be Sky and do like a 5.1 broadcast. So the process for extracting audio objects. Well, first of all, we've got to think about what we want to actually extract. What do we consider to be interesting audio in this case? Well, we propose that it would be mainly people kicking footballs. That sounds good. Referees blowing whistles, and potentially people, the sound of somebody running or shouting at each other. So what we have essentially been doing is listening, if you like, to all of the 12 shotgun microphone feeds with a computer and thinking, what is interesting in this? Can we match any of the audio in the microphone feeds to something that we would consider interesting? It's kind of like an audio pattern matching, if you like. So once we've determined which sections match up with either a whistle blow or a ball kick or something, then we need to extract that content, and then we also need to figure out where in the world was it on the pitch. We can hear it in these microphones, but we don't know exactly where the referee was standing when he blew his whistle. And we can do that either based on just a one microphone location. If only one microphone picks it up, then we don't have that much information, so we'll just have to position it somewhere near that microphone. But if more microphones pick it up, then maybe we can do more intelligent things and do some sort of triangulation, if you like, to pinpoint the exact position of it. So I'll briefly just go into how we do it for ball kicks and then also for whistle blows, just to whet your appetite for some of the work and hopefully illustrate some of the challenges. You can see I've got here a spectrogram of a ball kick, which is often a really useful way of looking at what's our audio signature, if you like. So you can see it's quite obvious, I would have thought, that I'll point to it just to get the blood going. Ball kick. You can see that it's characterised by the fact that there's not a lot of what you'd call transient energy either side, and then all of a sudden, boom, somebody kicks a ball. So that makes it fairly easy to extract to some extent. It's predominantly a low frequency effect, obviously, if somebody's kicking a ball full of air. So what we do is we apply a selection of filters essentially to the audio stream, so that we're looking for transient energy in particular frequency bands. If you look for transient energy in just one frequency band, then you may find you're picking up something completely different. Just happens to be a boost in energy at that frequency. So we're looking for a straight line in our histogram. So we'll do it for multiple frequencies. And what we do is calculate what the gradient is of that envelope, which is calculated using this power spectral density. So it's like a frequency representation, if you like. And we're looking at what the gradient is. If the gradient of that is above a certain value, this blue plot here is the gradient, then we know that the energy's changed really, really quickly. So it's probably not somebody speaking, it's probably something really impulsive. And if it happens at low frequency, it's probably going to be a ball kick. So once we've calculated the gradient and we've figured, yeah, that's happened really quickly, it's in all the right frequency bands, it's probably a ball kick, then we extract the signal using this envelope. And we can use techniques later on, as I'll say about with the positioning, to figure out, was it a ball kick or was it just somebody in the crowd banging a drum, because they sound surprisingly similar. But if we can position the source, then we know if it's on the pitch, if it is somebody banging a drum, then that is really interesting audio, because that means that there's a streaker on the pitch hitting a drum, which would be unusual. So for whistle blows, we do it slightly differently. We first of all split the signal into chunks, and we compute what's called the Kepstrom of the signal, which is kind of like the Fourier transform of the Fourier transform, or the magnitude of the Fourier transform, which is really handy for picking out harmonic content. It picks out sort of if there's a repetition in the frequency response, then it's got harmonic content. And if you can look for the frequency, the fundamental frequency of a whistle, and it's got this associated harmonic content, then you're very likely you've stumbled across a referee blowing his whistle. I didn't put the frequency response on there, but it's got quite a defined frequency structure, a referee's whistle blow, which is very handy for us to pick out this. And we use a kind of moving average approach in order to figure out how the Kepstrom changes, and if it peaks above a certain value, then it's likely to be a whistle blow. I've got a little video, which is very short, but you see that we've got the spectrogram on the right, showing our harmonic content that I was describing. So it's very, very clear. But if you looked at just the time domain signal, you'd never pick it out. It just looks exactly the same as noise. And then this is the computed Kepstrom, so you can see that as the referee blows his whistle, it peaks. So this is actually a recording from that match I mentioned. I mean, we were lucky in this case because the referee was stood quite close to the microphone, so it's quite pronounced. So this is one of the pitch side mics. Positioning the sources is an interesting task. Like I say, if it's picked up in lots of different microphones, then it gives us a lot of information, and we can triangulate it. If it's just picked up by one microphone, then maybe we have to concentrate on one of these zones and position the mic in the middle, the sound in the middle of one of the zones to kind of minimize the error. So what we do is we look at the cross correlation. We look at how similar these two sounds are. So if I pick out something interesting in microphone 1, then I might listen also to what's going on in microphone 2. And if at the same time instance I have two signals that are highly correlated, they're very similar, then they'll be the same signal. And what I can do is I can use that cross correlation to find out what the delay is between one and the other. And that delay allows me to plot a sort of hyperbolic path of potential source positions. And if I've got 3 microphones, for example, then hopefully those two hyperboles should meet, and we should know where our source is, which hopefully will be illustrated by this. This is measured data. This is me running around in a field in Salford with a whistle and 4 microphones. So these, I'll play it. This is a whistle blow at 4 microphone positions. Not tremendously illuminating. And then these are my cross correlations. So you see you get a really strong peak, and it's the position of that peak that allows me to plot these potential source positions. And you can see I've nailed it there to within sort of 50 centimeters or so. So it's potentially quite an accurate system, but it does depend on how many microphones are picking up the sound at any one time. And we can also do this in real time, which means that we could implement that automatic mixing thing that I was talking about. So just to summarise then what I've said from an audio point of view, we look at mainly at an object-based approach. We're looking at audio objects and a sound field to provide the reproduction end with all the jigsaw pieces to put everything back together so that we can interact with the content and that so we can reproduce it format agnostically. And I've just spoken briefly about some of the ways in which we can extract audio objects. That was a football scenario, but if you were doing it for a theatre production, then you might want to use some kind of voice activity detection or speech recognition to find out who was speaking when, or you might also put some sort of tracking software, local GPS or some Bluetooth tracking to do that. Or, as we described, you can do it using this time difference of arrival approach, where you can plot the different hyperbole. But that's us done from an acquisition point of view, and I'd like to invite any questions that you've got for myself or Graham.